In this video, we're going to work through an example of using variation of parameters to solve a linear second-order inhomogeneous ODE with variable coefficients. To do this, we're going to need two linearly independent solutions to the homogeneous equation. If we're only given one, we'll need to find the second using some other technique, such as the reduction of order technique, and I'll put a link up for that video now. As a quick overview, we'll first need to rearrange the ODE until it's in the correct form shown at the top of the screen. Then we'll need to find the Wronskian W, shown in orange, and then we can solve for the particular solution y sub p, shown in blue. And finally, we can write the general solution using the homogeneous solutions plus the particular solution. So let's get into the example. Here we have a second-order linear inhomogeneous ODE with variable coefficients, so we can use variation of parameters. Our two solutions to the homogeneous ODE, y1 and y2, are shown below in blue. Step 1 is to always make sure that the ODE is in the correct form, where y double prime should be by itself. So in this example, we need to divide by x times x minus 1. Cancelling some terms, we end up with y double prime minus 1 over x minus 1 times y prime plus 1 over x times x minus 1 times y equals x minus 1. Now that it's in the correct form, we can let g of x equal x minus 1, or the right-hand side of the ODE. Step 2 is to find the Wronskian W. To find this, we use the two solutions to the homogeneous ODE, y1 and y2, and set it out in a matrix where y1 and y2 make up row 1, and y1 prime and y2 prime make up row 2. The straight lines on the side just means we'll be finding the determinant of the matrix. So we get x times ln of x plus 1 minus 1 times 1 plus x times ln of x. And this just simplifies to x minus 1. On a side note, if our determinant ever equals 0, this tells us that our two solutions are not linearly independent and we can't proceed any further with our current y1 and y2 values. Step 3 is to find the particular solution, y sub p, using the formula minus y of 1 times the integral of y2 times g of x over w plus y2 times the integral of y1 times g of x over w. Just to recap, our g of x equals x minus 1, or the right-hand side of our ODE. W also equals x minus 1, although w doesn't usually equal g of x. It does in this example. And y1 equals x, and y2 equals 1 plus x times ln of x. Just a note, it doesn't matter which solution is y1 and which solution is y2, we'll get the same answer. Now we just plug in the values, calculate the integrals, and simplify. You may need to use integration by parts, use substitutions or trig substitutions. Here I'm using integration by parts, or the DI method, which has the same result. The D just stands for derivatives and the I stands for integration. Simplifying and cancelling terms, we end up with our particular solution y sub p equals 1 over 4 x to the 3 minus 1 over 2 x to the 2. Using our solutions to the homogeneous equation, y1 and y2, we can write the general solution y equals c1 of x plus c2 times 1 plus x ln of x minus a half x squared plus 1 over 4 x to the 3 for some constants c1 and c2. If you liked the video, then please give it a thumbs up. If you found it helpful, then feel free to subscribe. I make regular videos on calculus, linear algebra, statistics, psychology, and physics. As always, thanks for watching.